back, folks. Continuing our chapter on prob and stats, we're talking more statistics today. In section 1.6, we're talking about normal distributions. Now, for the last few sections, we've looked at some different distributions. Okay, we've talked about their shapes and some way of describing them. Here in 1.6, we're going to look at a very specific type of distribution and some properties of it that allow us to answer questions, solve problems related to it. Okay, so here we go with that. To get us thinking about how a normal distribution works, I'm going to look at a very simple example, a dice rolling simulator, where what this simulator is going to do is randomly generate a pair of dice rolled and then keep track of what my outcomes are in histogram format. And it's also going to let me roll multiple dice at a time, so when I push this button, it can do 10 at a time. Okay, now we can think of dice, but we can also compare this to average heights or shoe sizes or IQs. Okay, if we think about kind of a small sample set of 35, so for example, the heights of 35 students, we're not always going to get what we'd expect to be average, or an average result. Okay, for example, here it looks like there's kind of a lot of taller people if we thought average height compared to shorter people. Okay, but as the more I roll the dice, or in other words, the more people I looked at, so for example, we looked at hundreds at a time, I'm going to click up to about 1295, so for example, the entire school population at New Prague, things would start to even out. We'd start to see the average heights, okay, take over, and then tail off as we get too taller, and tail off as we get too shorter. Okay, we get this symmetric shape, and in general, we'd expect that not to change even as we add 10,000 rows, as we looked at several high schools at once. Okay, we get this nice even symmetric distribution. Okay, in general, data that follows this type of bell curve, this type of symmetric distribution, we'd say follow a normal distribution. So when I say normal distribution, we're talking about this bell curve shape. Okay, what basically makes it normal is when the mean, okay, the average, is equal to the median, which is also the center, which is equal to the mode, the most common. Okay, when that mean, median, mode all line up in the center, we get a symmetric shape on both sides. Okay, essentially, we're looking at a normal distribution. Okay, there's a lot of things in the real world that are normally distributed. Like I said, heights, okay, shoe sizes, IQs. We'll look at a few different examples as we go through today. Okay, one thing to remember about it is it's not just a single curve. Okay, it's a family of curves, and the shape is determined by the mean, the x bar. Okay, so where that mean lies, and its standard deviation. Okay, the spread about the mean. We'll say the x bar determines where the peak occurs. Okay, so our higher mean is going to make that peak occur more to the right, lower mean to be to the left. Okay, and the standard deviation determines how spread out it is, okay, how fat this curve would be or how skinny it would be. So quick problem here to get us thinking about the mean and standard deviation of normal distributions. Okay, problem 1 asks which normal distribution has a greater mean and standard deviation. Okay, so I have two normal distributions next to each other. Okay, we can think of these as, let's say, average heights of females and males. Okay, we know that males are typically taller than females. Okay, I'm not sure which one's spread out more. We'll just use that as an example. Okay, these two different graphs have two different means. We could say that where the first graph peaks is x bar sub 1, okay, the mean of the first graph. And x bar sub 2 is going to be where the second graph peaks. As far as comparing these two means, then I'd say that x bar sub 1 is less than x bar sub 2, okay, because I can see that the mean of the second graph occurs farther to the right, okay, at higher numbers than the mean of the first graph. Okay, we can also think about the standard deviation, okay, the spread about the mean. Now, since my first graph is wider, it's more spread out than the second graph, I'd say my sigma, okay, for standard deviation sub 1 is greater than sigma sub 2. Okay, again, here that's just saying that this first graph is wider, it's more spread out than the second graph. Okay, so when we're talking about family of curves whose shapes are determined by the mean and standard deviation, that's what we're talking about here. Now, as far as answering questions about normal distributions, there's going to be a property that they all have in common that allows us to do it. Okay, that's going to be, we'll say, the 68, 95, 99.7 rule. Okay, it says for all normal distributions, 68% of observations fall within one standard deviation of the mean. Okay, in other words, if I have the mean at 0 here, and I count up one standard deviation and down one standard deviation, 68% of my observations are going to fall within that one standard deviation. Okay, 34% on the right and 34% on the left. Okay, so if we're thinking about average heights again, if we know the standard deviation, we know that 68% of men's heights, for example, would be between one standard deviation. Okay, 34 on the right, 34 on the left. All right, continuing, 95% fall within two standard deviations of the mean. So if I count up two standard deviations on both sides, that's going to contain 95%. When I subtract out the 68% in the middle and divide that by 2, I get 13.5% between one standard deviation and 2 going up, and then the same 13.5% between -1 and -2 going down. And then by the same manner, 99.7% fall within 3 standard deviations of the mean. So if I go from 3 up down to 3 up and subtract out the 95% in the middle, divide by 2, I'd end up with a 2.35% on the left, 2.35% on the right. And again, this will be true for all normally distributed data sets. Okay, average heights, average weights, anything that's normally distributed is going to follow this pattern here. Now, typically students don't memorize the 68, 95, 99.7 numbers. What they'll do is they'll remember the 34s, the 13.5s, and the 2.35s. Okay, those are going to be numbers you'll need to memorize for test time and apply to different questions. We'll show you how to do that in 1 second here. So let's take a look at how we can use that 68, 95, 99.7 rule to answer questions here. Okay, problem 2 says the height of American males is normally distributed with a mean of 69.5 inches and standard deviation at 2.5 inches. Okay, like we said before, if we know the mean and standard deviation, we won't know what this curve is going to look like. Okay, so what I'm going to do is I'm going to sketch that curve, and I'll use that info to solve the different questions or answer the questions you see below in your note guide. Okay, so let's start off by sketching that curve here. I'm going to make a rough shape of a bell-shaped curve. Doesn't need to be perfect. Okay, and info says that the mean is at 69.5. So I'm going to draw a 69.5. Okay, where the peak of this graph is here. And then its standard deviation is 2.5, so what I'll do is I'm going to count up one standard deviation and say that, and add 2.5 to the 69.5, which gives me a 72. Okay, so the meaning that my next standard deviation will be at 2.5 plus 72 would be a 74.5. And then going up a third standard deviation would take us to a 77. And typically the percentage of observations that are outside that third standard deviation are so small you're not going to count up beyond that. Okay, we'll count backwards though. If we go 69.5 minus 2.5 to go down to one standard deviation, that would give me a 67. Okay, 67 minus 2.5 will give me a 64.5. Okay, for two standard deviations below the mean. And going down one more standard deviation, minus 2.5 again, we'll get a 62. The reminder, these are all in inches here. Okay, what I can do with that is I can apply my 68, 95, 99.7 rule and kind of fill in those percentages we know. We said there were 34%, okay, from the mean down one standard deviation, and 34% for the mean up one standard deviation. we said that between 2 and 3 there was a 13.5% of the observations. And then from 2 to 3 we said there is a 2.35%. Alright, once we have that all kind of mapped out, drawn out, we'll be able to answer some different questions, okay, about the average heights of males. So looking at question A, it says what percentage of American males are between 67 inches and 74.5 inches? Okay, so we want to know what percentage of the male population fall between 67 inches, which is 1 standard deviation below, and 74.5, which is 2 standard deviations above the mean. Okay, and to do that, what we'll do is we'll just add the percentages that fall kind of within each of those chunks of this graph. So in other words, 34 plus 34 plus 13.5. Okay, when I add all that together, I get an 81.5%. Okay, meaning 81.5% of American males fall between 67 and 74.5 inches. Next question, part B, says what percentage of American males are taller than 74.5 inches? Okay, so if I find my 74.5 here, I want to figure out what is above, okay, what percentages make up from 2 to 3 standard deviations and 3 and above. Okay, now we didn't give you a spot here to memorize, so one thing we could do is figure that out. Otherwise, the thing we could do is we could take the 50% for everything above the mean and then subtract out the 34% that we're not including and the 13.5% that we're not including. And that's going to give us everything above, which leaves us with a 2.5%. Okay, so 2.5% of American males are going to be above that 74.5 inches. Okay, now another way we can do this question is memorize what comes above the third standard deviation. Okay, it looks like it's 2.5 above 2 standard deviations. So if I go 2.5 and subtract the 2.35, what I end up with is a 0.15%. Okay, I'm not a fan of memorizing extra stuff, but if you're good at memorizing, okay, one other way you could do is memorize that it's 1.5% above 3 standard deviations, leaving it's also a 0.15% below. Okay, that'd be an alternative way to do this question. Part C asks, what height is at the 16th percentile? Okay, in other words, which height has 16% of the population below it? Okay, for that what I can do is just start adding up percentages till I get to 16%. Okay, remember we just found that from 3 standard deviations down and below is a 0.15%. So if I go 0.15 plus 2.35 plus 13.5, okay, that just happens to be equal to 16. Okay, meaning that this chunk of my graph accounts for 16% of the population. Okay, so 16% of the population is below 67 inches. Okay, so we'd say that 67 inches, okay, is at the 16th percentile. Okay, with percentile being percent below. D, last part for problem 2, asks what is the percentile rank of a 77-inch tall American male? Okay, percentile rank, in other words, what is the percentile of somebody that is 77 inches tall? Okay, so what percentage of the population is below them? Okay, so here's my 77. All I need to do then is add up all percentages below it. Okay, I can take care of the first half of the graph by just knowing that 50% is below the mean. So if we go 50 plus the 34, all right, plus 13.5 plus the 2.35. Okay, add all that together, we get a 99.85. Okay, so we'd say the percentile rank of a 77-inch tall American male is 99.85. In other words, 99.85% of the population is below that height. Okay, that's the basic idea of using that 68, 95, 99.7 rule to solve problems. Okay, now we're only going to ask questions about numbers that fall on the standard deviations. Okay, getting in between them, that'd be something we'll save for a statistics class. That'd be a lot tougher. Okay, but problem 3 is the same idea. Why don't you pause the video, okay, take a minute to draw out that curve, okay, and then hit play to check your answers. Alright, hopefully you paused the video and took a minute to try these ones. Okay, problem 3 says ACT test scores are normally distributed with a mean of 21 and standard deviation of 4.5. Okay, so I'll draw my bell curve. I'll put 21 at the center for the mean, and I'll just count up by 4.5, 3 standard deviations, and then count down by 4.5, 3 standard deviations. And then part A says what percent of students score between 21 and 30. Remember, to figure that out, we'll just add up all the percentages that lie between the 21 and the 30. So that would be a 34% plus 13.5, which gives us a 47.5. So we can say percent. Part B, what percentage of students scored above 34.5? Okay, 34.5 is 1, 2, 3 standard deviations up above from the mean. Now remember, we can memorize that value is 0.15, or we can take the whole thing 100, subtract the 50% below the mean, the 34%, the 13.5%, the 2.35%, and come up with that 0.15% through subtraction as well. Part C asks what value is at the 84th percentile. Okay, in other words, what score has 84% of the population below it? Okay, for that, what we'll do again is just start adding up percentages until we get to that 84%. Okay, once I get this second 34 added up, so 0.15 plus 2.35 plus 13.5 plus 34 plus 34 will give us that 84. Okay, so we'd say a score of 25.5 is at the 84th percentile. Last question then, what is the percentile rank for a score of 12? In other words, what percentile is 12 at? What percentage of the data is below 12? Okay, for that we'll just add up everything below, the 0.15 plus the 2.35, that gives us a 2.5 percent. So we'd say that 12 has a percentile rank of 2.5%. Alright, that's it for section 1.6. Okay, give the homework a shot. If you have to rewatch any portions of the video, go ahead and do that. Okay, otherwise, like usual, if you need to come in for some extra help, for some questions, anything that's not clear to you, okay, we'll be here in the morning or after school.